Hi everyone. So in today's video, we're going to actually get back to talking about tangent lines. So we're going to return to some of the ideas that we were talking about on the first video of class. And now that we have all of these different techniques built up from limits, we'll be able to find the slope of tangent lines in a nicer way. Um, so I just want to quickly say I mentioned this in the notes or the description of yesterday's video, but I'm sorry that I know the audio has been kind of up and down lately. So I've probably talked about this in other videos, but yeah, basically my laptop has really not a good microphone. So I'm using some headphones that also sometimes seem to have a fine microphone, but other times it's not so good. And then I ordered an external lapel microphone on eBay, or sorry, not eBay, Amazon. And it arrived last week, but it didn't work, just defective. And so I just ordered a new one. So we'll see if that works. So bear with me. Hopefully I'm at least somewhat audible in this video. Okay, so we are going to be in now section 2.7 in the book. And so this is going to be our first discussion of something that's called a derivative. And so we'll get to what that means in a little bit. So I want to go back to one of the first examples that we actually used when we were talking about finding the slope of a tangent line. So if you remember, we did the example of f of x is equal to x squared. And we were trying to figure out what is the slope of the tangent line at x is equal to 1. So we kind of sketched this tangent line and tried to guess what it looked like the slope was. And then in order to find that slope, we use secant lines. So the idea was that we would take another point on the graph, like close to an x value of 1, and find the slope of the line between those 2 points. And so as we brought that second point closer and closer to 1, that would give us a better and better approximation of the slope of the tangent line. So let me just quickly show you again on Desmos this visual that I made. So here's the graph of the parabola that we had on the other page as well. So this is f of x is equal to x squared. And so you can see that, so here's the second point where that I'm using for the secant line. And you can see that as I bring that second point closer, and maybe let me see if this is clearer if I do it like that. Yeah. So as I bring the second point closer to 1, notice that this red line pretty much looks like it's exactly the same as the tangent line. And then if I bring it further away, it gets further away, bring it closer, it gets closer. So we're going to take that idea of bringing the second point closer, and we're going to kind of restate that idea in terms of limits. And it makes sense because if you think about, what were you doing with these types of problems? You were plugging in a bunch of different numbers, getting closer and closer to something. And that's exactly the same thing that you were doing when you first started with limits. And so now that we have all of these different algebra tools that we can use for limits, we can use those same algebra tools to find the slope of a tangent line. So the way that we're going to set this up, so let me start by writing a couple things down. And oh, yes, my mouse wasn't working earlier, but just started working, thankfully. Just going to move this over a little bit. Okay, so basically just to kind of restate something that I was just rambling about a minute ago, we said that the slope of the tangent line at x is equal to 2 is equal to, and this is going to be kind of like a not super technical way of writing it, but I'm going to say it's equal to the slope of the secant line from x is equal to 2 to x is equal to b, bringing b closer and closer to 2. So this is, again, not like a super technical mathy way of saying it, but basically, you might think, why am I saying the slope of the tangent line is equal to the slope of the secant line? You're right, it doesn't quite make sense, but I'm basically just trying to kind of state the idea of a limit without actually writing the word limit. So that's where the bringing b closer and closer to 2 part comes in. So there's another way that we can say this that's going to be useful for writing stuff in terms of limits. So looking at the picture that I have here, so we have our x value of 1, and sorry, we're not working on the slope of the tangent line at 2. Sorry about this. This must be confusing. Let me fix that. When I wrote up my notes for this class, I thought we were doing it at 2, and then I looked back and on the previous lecture, I realized it was at 1. So sorry about that. So all those times I said 2, I meant 1, because that's where we're actually doing the tangent line. So if we look at 1, that's the place where we're actually doing the tangent line. And then the other point, we're calling that b. So if I go down here, it looks like as it is right now, this x value we're calling b. And so what are we doing with b? We're bringing it closer and closer to 1. And by the way, we could have also done a value of b that was over here. I'm just drawing it to the right just because I had to pick one side or the other. So yeah, but just keep in mind that it could have been on the other side. So there's another way to think about this number b. Instead of calling it b, I'm going to call it something else. I'm going to call it 1 plus h. And so why am I calling it that? It's basically because we know that that point is close to 1, right? We're choosing the second point to be close to 1. So I'm calling it 1 plus h to represent like 1 plus a little bit extra. So I'm going to kind of write that down here. So instead of finding the slope from 1 to b, we're finding the slope of the tangent line, or sorry, the secant line from x is equal to 1 to x is equal to 1 plus h. And so this part is kind of important. So I want you to think for a second about how could we kind of rephrase this idea of bringing b closer and closer to 1? What would we be doing with h? So if you think of h as being like this extra little bit amount that you're adding on, or h could also be negative, in which case you'd have a point on the left. But think about what number you want to bring h closer to. If you're trying to take 1 plus h and bring it closer to 1, what would that say about h? So that would mean that we're trying to bring h closer and closer to 0, right? Because the closer that h gets to 0, that means that you're just taking 1 and you're adding on like 0.1 or 0.001. So h is just that kind of little bit extra. You can think of h as like how far are you actually away from your point? How far are you away from 1 in this case? So now that we've written down in this language with this h thing, now we're going to be able to rephrase this in terms of a limit. And by the way, there is a way to write the way that, so if you go back to how it's written here, there is a definition using limits that uses that idea, but for the sake of simplicity, I just like to use the second one because usually the algebra for it works out a little bit nicer. So I'm going to leave some space here because we're going to add in the limit part in a moment, but I want to just first write out the other part. So I'm going to write something down, and then we'll talk about where it's coming from. Okay, so what is that I just wrote down? Well, it's the slope of the secant line from 1 to 1 plus h, right? The slope of the secant line between two values is the change in the y values divided by the change in the x values. So the y values, so our x values are 1 and 1 plus h, and we get the y values by plugging those in. And then in the denominator, we have our x values. So you don't need to put parentheses here, but you could. 1 plus h is one of those x values, and then 1 is the other x value. So this part here is the slope of the secant line from x is equal to 1 to x is equal to 1 plus h. And then again, we're gonna leave some space because we're gonna add in this limit idea, but I just want to simplify this a little bit. So we can simplify this because in the denominator, we are just left with 1 plus h minus 1, that's just h. So what is the limit part of this? Well, we said that we're trying to bring h closer and closer to 0. And so that tells us that we want to take the limit as h approaches 0 of this. And so same thing over here. This is the limit as h approaches 0. So this limit part comes from the fact that we're bringing 1 plus h closer and closer to 1, right? Because if that h part is getting smaller and smaller, then the point is getting closer to 1. Okay, so this is the formula that we're going to be working with, and I'll kind of write this out in general in a little bit, but this is going to be the general way that, at least for now, that we're going to be finding the slope of the tangent line. So let's actually go through and do that for this example. Then I'll write out what the general definition is, and then we'll do a few more examples. And we'll see that for like all of these examples, it's basically just using the same limit techniques that we've already learned. So if we wanted to find the slope of that tangent line, we're doing the limit as h approaches 0 of f of 1 plus h minus f of minus f of 1 over h. So for this specific function, our function was f of x is equal to x squared, right? So that's the function that we're going to be plugging in 1 plus h and 1 to. So f of 1 plus h is going to be, I have to make sure I don't forget the limit part, limit as h approaches 0. It's going to be 1 plus h squared minus 1 squared, right? That's our function, is just it takes the input and squares it. So this might look familiar to you as this is like the expand and simplify type of limit. So we're going to multiply everything out and see what can cancel out. So 1 plus h squared is going to be 1 plus 2h plus h squared. And then we have minus 1 all divided by h. And then we can simplify that further. So the 1's are going to cancel out, and we're left with 2h plus h squared divided by h. And so this is what should generally happen and we'll see this happen in some other examples too in different ways, but this h, so maybe going back to the beginning when we first had it written like this, or maybe it makes more sense to think about when we had it written like this. We could not plug h in, right? Because then you would have divided by 0. And so just like in all the limits we've been doing in this kind of same style, the goal is to use algebra to simplify your limit so that you can actually plug in the number. So what happened here is that those 1's canceled out. And so we're going to be able to factor an h out of the two things in the numerator now. So we're left with 2 plus h divided by h. So now these h's go away and we're left with the limit as h approaches 0 of 2 plus h. And now we can finally plug in 0 for h, right? Because now we're back, now we're down to something that is totally fine to plug in 0. So we get 2. And if you look back to the very first video, that's the same exact thing we found in for that slope. So that we now have really kind of shown for sure that that's the slope of the tangent line. Okay, so let's do some other examples. Actually, before that, I'm going to write out a general definition here. So it turns out there's a new notation I want to show you and a name for this slope of the tangent line idea. So this is now going to be kind of general fact. So in general, so the way that we're going to write down when we're talking about the slope of the tangent line at a particular number is we're going to write the name of our function, so f or g or h or whatever the function is. Then we're going to put this little dash or like apostrophe symbol, And then inside the parentheses, you put whatever number you're talking about. So in the example we just did on the last page, it was 1. So that number a is the x value where you're actually finding that slope. So how do you read this out loud? You can read it as f prime, so that that little like dash or apostrophe symbol is pronounced prime. So f prime of a is the way you would read that out loud. And what is f prime of a? What's the name of that? It's called the derivative of your function f, or f of x, either way is fine, at a, or at x is equal to a. So the derivative of f at a. And what is the meaning of this? What does this have to do with what we're talking about? It's basically just the fancy name for the slope of the tangent line. So it's called the derivative of f of a, and it is equal to the slope of the line tangent to your function at a particular x value. So for example, just to call up the example that we just did, in the previous example we just saw, we saw that if your original function is f of x is equal to x squared, then we found that the slope of the tangent line at 1 is equal to 2. So you would write that as f prime of 1 is equal to 2, and that's because we found that the slope of the tangent line at x is equal to 1, I guess I don't need a comma there, is 2. Okay, so let's write out now the full-on definition of the derivative. So this is what's sometimes called the limit definition of the derivative. And it's basically exactly what we just did in the last problem, but I'm just going to write it out in a more kind of general form. So f prime of a, which we know means the slope of the line tangent to f of x at a, is going to always be equal to the limit as h approaches 0 of f of a plus h minus f of a divided by h. So I know that there's a lot of symbols going on in this, right? We have a, we have h, we have the limit, we have f prime. There's a lot of stuff going on. But I really hope that, like I could have made this video a lot shorter if I just started by telling you this was the definition, right? But I really wanted to, on the previous page, give you an idea of why this is the definition. And I hope that that helps you remember it. So how should you remember this? Think of this part, the right part, the right-hand side, think of that as the slope of the secant line between a point that is close to a, so a plus h and a, and then the limit part is that idea of bringing that second point closer to the point A. Okay, so let's do some more examples. And we'll see that these examples are all going to bring in these different methods we have for evaluating limits. So let's let f of x be equal to square root of x plus 1. And we are going to find f prime of 3. So f prime of 3, according to the definition that we have above, and maybe I'll put like a box around this because it is very important. So f prime of 3 is going to be equal to the limit as h approaches 0 of f of 3 plus h. So I'm just replacing a with 3. And then the h stays there because that's our variable, essentially. And one thing that I think is nice, and especially as you get into slightly more complicated functions, rather than trying to do everything at once, I kind of like to figure out the numerator first, kind of separately. So we can first figure out what is f of 3 plus h and f of 3, and then kind of put them back into the limit so that we're not doing everything at once. So f of 3 plus h is going to be the square root. So we're replacing x with 3 plus h, right? That's how functions work, is whatever's inside the parentheses, we're replacing x with that. So we're replacing, sorry, I just wrote x instead of h. We're replacing x with 3 plus h, but then we still have a plus 1 because that's just part of the function. And so this can be simplified. 3 plus h plus 1, we could also rewrite that as square root of 4 plus h. F of 3 is just plugging in 3 to our function, so that's square root of 3 plus 1, so that's the square root of 4, which is 2. So now that we have that part, we can just kind of stick that into our function so that it's not as complicated, or we don't have to do it kind of all at once. So we have, in the numerator, we have the 4 plus h, or square root of 4 plus h, and then we have minus 2, all divided by h. So if we were in class in person, I would now pause and say, what are we going to do here? What method do we want to use? But I'll just tell you. So we're going to multiply by the conjugate, right? So this is where we think of those kind of, I guess it was like 4 major methods. So there's multiplying by the conjugate, there's making a common denominator, there's factoring and canceling, and then there was the expanding and canceling. And that was what we did in the last one. I noticed someone in the discussion board asked kind of like, how can you figure out what method to use where? And really, it just depends on what your function looks like. So in this case, because you, like basically, if you see a square root, that's what tells you that you want to use this conjugation method. So we want to multiply by the conjugate. So we're going to multiply the numerator and the denominator both by the conjugate, which remember, you leave this the same. That's not going to change. You only change the sign between the two parts. So this is going to become square root of 4 plus h, or sorry, 4 plus h plus 2. And this is square root of 4 plus h plus 2 as well. Okay, so when you multiply by the conjugate, you don't have to write out all of that multiplication because if you can remember that it's a difference of squares, basically all you're doing is the square root parts are going to multiply together, and that will cancel out the square root. So you'll have 4 plus h. And then the part that is not in the second part, those also get multiplied together, and those get subtracted. And then in the denominator, and this I mentioned is definitely a place where people can make mistakes. Don't multiply it out, just leave it as it is, because if you multiply it out, you're going to kind of rob yourself of being able to see what can be simplified. So now we have the limit as h approaches 0 of, so notice that in the numerator that those 4s are going to cancel out, so we're left with h divided by h times the square root of 4 plus h plus 2. So I always forget to mention this, but going back earlier in the problem, we never could plug in 0 for h, right? Because we have h in the denominator, we still have our h in the denominator, and so now we can see that we'll be able to cancel out this h, and that's what will help us to be able to actually plug in 0 for h. So we're going to be left with now the limit as h approaches 0 of 1 over the square root of 4 plus h plus 2. And now we can actually just plug in 0. So we're going to get 1 over square root of 4 plus 0 plus 2. So that's going to be 1 over square root of 4, which is 2 plus 2. So we're going to get 1/4. And so that tells us that the slope of the line tangent to our graph at x is equal to 3 is 1/4. All right, let's do another example that will bring up another method. So let's find, let's let g of x equal 1 over x, and let's find f prime of 2, or sorry, g prime of 2. Okay, so g prime of 2 is going to be equal to the limit as h approaches 0 of g of 2 plus h minus g of 2, all divided by h. So going back to that same definition above, just putting in now 2 for our a. So again, let's maybe go off to the side and figure out what g of 2 plus h and g of 2 are. So g of 2 plus h is going to be 1 over 2 plus h, because we're just putting in whatever's inside the parentheses for our x, and then g of 2 is going to be 1 over 2. So let's put that stuff in here. So we're going to get the limit as h approaches 0 of 1 over 2 plus h minus 1 over 2 divided by h. So I would say that this style where you end up with fractions, this is probably like the one that has the trickiest algebra to it. And actually, let me rewrite this so I have a little bit more space. So we have 1 over 2 plus h minus 1 over 2. And I'm leaving some space because we're going to have to make a common denominator, and I want to be able to write that in there. So you might look at 2 plus h and 2 and think, oh, those are very similar. Like I should be able to just kind of like add h to the 2 or something like that. But really, 2 and 2 plus h do not have any common factors. And so the only way to make a common denominator is to multiply them together. And that you can just kind of use that as a general rule for these types of limit problems. So we're going to multiply the first fraction by 2 over 2. And we're going to multiply the second fraction by 2 plus h over 2 plus h. Because then both of them will have the same denominator of 2 times 2 plus h. So we have the limit as h approaches 0 of 2 over 2 times 2 plus h minus 2 plus h over 2 times 2 plus h, all divided by h. And I know that this is going to look kind of intense and scary, but don't worry, we will get to a point where it gets more simple. So let's we made a common denominator. Let's actually put those pieces together. So if we put the two numerators together, and you have to be really careful here, so pay attention. So if you're subtracting a fraction from another fraction, and the fraction that you're subtracting has two terms or more than one term in it, you have to put parentheses around that and make sure that you're subtracting everything in that numerator. Otherwise, this will not work and you'll get the wrong answer. So our new numerator is going to be 2 minus 2 plus h, all divided by 2 times 2 plus h, and that's all divided by h. Okay, so let's simplify that numerator within our numerator. So the numerator is going to be 2 minus 2, which is going to become 0, right? And then we have minus h. So we're left with negative h over 2 times 2 plus h over h. So we can rewrite this a different way that will help us see what can be simplified. And this is kind of a general trick that's oftentimes really useful, is when you're dividing, instead of writing it as division, rewrite it as multiplying by the reciprocal. So we can rewrite this as negative h over 2 times 2 plus h, and then multiply that with 1 over h. And that helps us to see that we have an h in the numerator, h in the denominator. We can cancel those out. And so we're getting close now, because now we have the limit as h approaches 0 of negative 1 over 2 times 2 plus h. Okay, so what is going on here? Well, again, looking back earlier in the problem, we had an h, we had an h, we always had an h in the denominator, and now we finally don't have that h in the denominator anymore. And so now we can actually plug in 0 for h. And so we'll get negative 1 over 2 times 2 plus 0. And so that's negative 1 over 4. And so that tells us that the slope of the line tangent to the graph of 1 over x at x is equal to 2 is 1 over 4. Okay, so there's one more thing I want to throw into the mix here, and that's actually coming up with the equation of the tangent line. So when I say that, what I mean is basically if we go back to this original picture, for example, um, and we look at the green line that I have, the tangent line, that line has an equation, right? Just like any line, you can write the equation of the line. So in this case, I mean, I didn't draw it that well because this bottom part I think should go a little more like that. But we could actually figure out the equation of this line just by looking at it, right? It has a slope of 2, it has a y-intercept of negative 1, so the equation of this tangent line would be 2x minus 1. And so we can do the same thing without, in that case, we're just literally looking at the graph, but we can do that without having the graph in front of us for these other problems. So before we do an example, I want to kind of remind you of a few things. So, it can be kind of a review, equations of lines. So I found that when I get to this section and we're talking about finding the equation of the tangent line, for some reason, this is one of the topics that a lot of students struggle with all throughout the quarter. I try to really keep working on it all throughout the quarter, and a lot of students just kind of come back to this as a topic that they just, I don't know, never quite clicks. And I think a lot of it is that people just get kind of overwhelmed by all the different things that are floating around. So I want you to really, when we're talking about the equations of tangent lines, go back, pretend that you're in a basic algebra class. Whatever class you first learned how to write an equation of line, take yourself back to that place and think about, what's the information I need in order to write a line, and that's really all you're doing. So there's two different formats of equations of lines. I mean, there's others too, but there's two main ones. So the first one that you may have learned is what's called slope-intercept form. So that is what's like y is equal to mx plus b, where m is your slope and b is your y-intercept. So we're actually not really going to be using that form as much. We'll sometimes put things eventually into that form, but there's another form that's actually going to be much more useful to us, and that's what's called point slope form. So for slope intercept form, you need to know the slope and you also need to know the y-intercept. And so point slope form is something that's useful if you don't know the y-intercept, if you just know some other random point. So point slope form looks like this. You have y minus y1 is equal to m times x minus x1, where again here m still is the slope, and you know that your line goes through the point x1, y1. So you're basically, you have a point that you know your graph goes through, and you're just subtracting the x coordinate from x, and then you're subtracting the y coordinate from y. And by the way, kind of just a side note, this, if you ever kind of forget this form, it basically comes from the following. So if you want to find the slope between points, you subtract the y coordinates. So let's write that as y minus y1. And in the denominator, you subtract the x coordinates. So if you take this equation and you multiply both sides by x minus x1, you get m times x minus x1 is equal to y minus y1. So maybe that will help you remember point slope form. So like I said, this is going to be really important. We're going to be using this all the time. Okay, so let's say that we wanted to find, so let me start a new page here. So finding the equation of a tangent line. So basically, based on what we just saw on the previous page, we saw that for point slope form, you can write the equation of line with only two pieces of information. So the two pieces of information that you need are, one, to know the slope. So in this case, if you're writing the slope of a tangent line, you need to know the slope of the tangent line. And the second one is you just need to know a point that that line happens to go through. Okay, so let's look at an example, and we're going to do an example going back to one of the earlier ones that we did. So let's say that we wanted to find the equation of the line tangent to f of x is equal to square root of x plus 1 at x is equal to 3. So that one, we already earlier did a derivative for that one. We found f prime of 3. So if you think about it, if you're trying to find so if we already found f prime of 3, so maybe let me just write that fact down. So we already found that f prime of 3 was equal to 1/4. So let's think back to what f prime of 3 actually means. F prime of 3 means the slope of the line tangent to the graph at 3. So this is the slope of the tangent line. So we're halfway there. That's one of the pieces of information we need to write the equation of a line. So let me just kind of add that to what's written up here. So this is the derivative. And so now all we need is the point. So now we need a point x1, y1, which is going to be the point that goes into our point slope form. So we know that the tangent line goes through x is equal to 3, right? And let me actually pull up a picture here. So here is the graph of square root of x plus 1. So here we have x is equal to 3. And so we're looking for the equation of the tangent line to the graph at that point. So we can see based on this graph that the y-coordinate of the point is 2, right? We have 3, 2. But let's say we didn't have that graph in front of us. So how would you figure out what that y-coordinate is? So we know the tangent line goes through a point. I don't know why all those things are popping up, where x is equal to 3. So to find the y-coordinate, again, I think this is where, like, when you're in calculus, it's like you almost have too much knowledge. I want you to, like, go back, pretend you don't know anything about derivatives, and pretend someone said to you, here's your function. Here's your function. You have the function f of x is equal to square root of x plus 1. If x equals 3, what is the y-coordinate? You would say, oh, you just plug the x-coordinate into the function, right? So I've had, like, a lot of students in the past will get confused. They're like, oh, do I plug it in the derivative? Do I plug it in the function? What's going on? It's just think about what you're doing. You're looking for the y-coordinate on your actual function. So you just plug that number into the function. So f of 3 would be equal to square root of 3 plus 1, which is equal to 2. So now we know, so here we have our slope. So this is our m. And so now we know that it goes through the point 3, 2. And so this is our x1, y1. And so now we can write down our equation. So we're going to write down y minus y1 is equal to m times x minus x1. And so that means that y minus 2 is going to equal to 1/4 times x minus 3. And so this is fine. This actually, this is the equation of the tangent line. This is just written in point slope form. On your homework, they want you to write it in, like I think the way it's set up on the homework, it's just like y is equal to, and then you have to type into this box. So for that reason, you do have to know how to be able to take this equation and put it into slope-intercept form. So all you have to do is just multiply stuff out and move stuff to the other side. So y minus 2 is equal to 1/2 x minus 3/2. And now we can just add, and sorry, I don't know why I wrote 1/2. Sorry for all these mistakes there. Our slope is 1/4. I'm picturing that you're all just like yelling at your computer screen. So this is actually minus 3/4. Sorry about that. Okay, so now we can just add this 2 to both sides. So we get y is equal to 1/4 x minus 3/4 plus 2. And then 2 can be written as 8/4. So y is equal to 1/4 x plus 5/4. So that's what you would want to do for the online homework. They want you to write it, I believe, in that form. Okay, so we're pretty much done. Let me just quickly show you the graph again. So here was our original function. So I'm not sure I think with where the screen cuts off, you probably can't see this equation, but I typed in y is equal to 1/4 x plus 5/4. And when I graph that, we get that appropriate tangent line. So that is it for today. There's a worksheet with basically practicing this stuff more, plus kind of getting into some other ideas that we will pick up on next week. So I will see you next time and have a great weekend.